Now in this lecture and the following few other lectures, we will be talking about solving linear time invariant resistive circuits. Okay? By solving linear time invariant resistive circuits, we mean developing tools or developing methods through which we can, in a systematic way, formulate a given linear time invariant resistive circuit. Even though we will talk about those methods, or we will introduce those methods through this particular class of circuits, they are by no means restricted to this class. They are applicable, and we will apply them, as a matter of fact, for more general classes of circuits later on. Okay, but since we're now introducing those methods, it's best to introduce them through the simplest class of circuits, okay? LTI resistive circuits. So, of course, the first thing we should do is we should be clear about what we mean by LTI, linear time invariant resistive circuits. So that's how we will start this lecture with, okay? The precise definition of LTI resistive circuits. And then we will talk about some other definitions, okay? Or some other concepts that are essential for solving LTI resistive circuits, and also useful for other classes of circuits, such as the substitution theorem. And we will introduce the concept of a one-port circuit, and then we will talk about a very important notion of equivalence for a given pair of one-port circuits. And once those definitions are behind us, we will finally start our methods, okay, introducing our methods for solving circuits, okay, non-voltage analysis method and mesh current analysis method. But first, let's make sure that we understand when we use the word linear time invariant resistive circuit. Okay. So the first question we should answer, therefore, is what is an LTI? LTI is the abbreviation for linear time invariant. Okay, resistive circuit. Okay. Now we will define an LTI resistive circuit in a backward way, okay? By which I mean we will define what is not an LTI resistive circuit, and then through that description we will understand what we mean by an LTI resistive circuit. Okay, so a nonlinear circuit contains a nonlinear resistor or inductor or capacitor or a dependent source. Okay, DS for short. A circuit then is linear if it's not nonlinear circuit. So that's how we define the concept of linearity for a circuit. A circuit is linear if it is not nonlinear. Okay, so that's gone. How about time invariance? So we'll define time invariance by first defining time invariant circuit. This is our next definition. A time invariant circuit contains a time varying, TD for short, resistor or inductor or capacitor or a dependent source. Okay. And then the circuit is time invariant if it is not time invariant. Okay, so that's how we define time invariance or time invariant circuit. Okay, and then we'll define now what we mean by the resistive circuit. By resistive circuit, we simply mean that in order to be able to solve a circuit, if you don't need to integrate anything, if its description doesn't contain any differential equations, roughly speaking, that's what we call a resistive circuit. Okay, so a dynamic circuit contains a component whose description in terms of current and voltage is through a differential equation. And we saw two such components, inductors and capacitors. Therefore, a dynamic circuit, or what we mean by dynamic circuit, is such that a circuit that contains an inductor or a capacitor. Contains an inductor or a capacitor. And then the circuit is resistive if it is not dynamic. Okay, so by a resistive circuit we mean a non-dynamic circuit or a memoryless circuit. Okay, so that's therefore what we mean by an LTI resistive circuit. And for a while, that class of circuits will be our subject of study. Now let's introduce a very useful result that's applicable to LTI resistive circuits, but it's also applicable to some other class of circuits. Okay, which is substitution theorem. Okay. So consider the two circuits N1 and N2 11. In fact, those two circuits can be considered as two pieces of one single circuit. So let me draw it. Okay. Here is a piece of the circuit, and here is another piece of the circuit. Okay. So this piece we're calling N1, if you will. It's a sub-circuit of this whole circuit, and then we have the other piece, which we're calling N2. And then N1 and N2, they communicate with the outside world only through these two wires, and they are connected to one another. There are no other wires that are sticking out of those two boxes. Okay. And now these nodes, let's call them node A and node B. And then, suppose that this current here flowing in that direction is IT. We either measure it or compute it. Okay, IT. And this voltage here, we label it V of t. Okay, that's the voltage. Again, we either measure it or compute it. Now, substitution theorem says that if you know the current I of t or the voltage V of t, then You can replace this guy N2 with an independent current, so either independent current source, independent voltage source, and by choosing properly what the current or the voltage of the independent current source or the independent voltage source will be. And then after that substitution, N1 will not feel any difference. Okay, so more precisely what we mean is the following. We can replace sub-circuit N2, okay, by either an independent voltage source with voltage appearing across its terminals being equal to V of t, the voltage that's measured here or computed there, or by an independent current source whose current that it supplies, Is of t, equals the current that's flowing here in this configuration. Without affecting any branch current or voltage within N1 inside N1. Okay, so what is meant here in this statement is the following. Suppose that this is the original configuration. Let's call it configuration or circuit 1. Okay. And then here the claim made by the substitution theorem is take N1, the same sub-circuit over there. Okay, these are the nodes A and B. And then replace N2, take this N2 out, and instead connect a voltage source here. Okay. Vs of t. And Vs of t equals this voltage here that's measured or computed. Okay. Or what you can do is, okay, this is N1, A, B. We can also connect a current source, independent current source, whose current that in that direction equals the current that's measured or computed over that line of t. So this is the original configuration, and let's call these two configurations 2 and 3. And substitution theorem says that for any let's say imaginary person sitting inside that circuit N1, he or she will not be able to feel any difference between those three scenarios, okay? 1, 2, or 3. Everything inside N1 will be the same in all those three configurations. Okay? So let's put that informal explanation also. Okay? In other words, an observer inside N1 cannot tell the difference between those three configurations. Okay. Cannot. The difference between configurations or for circuits 1, 2, and 3. Okay. Now, having defined substitution theorem, let's introduce a very important and useful concept of a one-port circuit. That's our next definition. Okay, a pair of associated terminals is called a port. Okay, it is called and one port or a one-port circuit is a circuit or circuit element that has one pair of accessible from outside. So here we have a box, and inside the box we have a circuit, and that circuit, okay, you can have many resistors, inductance, capacitors, and some other components inside. And this circuit here inside our box has only one way of communicating with the outside world, and it's through these two wires. Okay, and that pair of wires, or that pair of terminals, we're calling a port. And this circuit or circuit element we're calling a one-port circuit, or in short, simply one port. Okay, and the voltage that we would measure across those terminals will be the port voltage of that one-port circuit, and likewise this current that's entering to the one port from one of the specified terminals is the current at the port terminals. Okay, and together voltage and current pair determine the port characteristics of this one-port circuit. One-port circuit. Okay. Now that, since there is no other way except for those two wires that this one-port circuit communicates with the outside world from KCL, this current here must be in that direction, I, okay? So that I, whatever enters from one of the terminals, must be leaving from the other terminal. Okay, simple consequence of KCL. And now, having defined what we mean by one port, we can now introduce the very useful and important notion of equivalence for a given pair of one ports. Okay. So that's our next definition. Two one-ports or two one-port circuits are said to be equivalent if they have identical current voltage relationship at the port terminals. Okay. Characteristics at the port terminals. So let N0, N1, and N2 be 3 one-ports, and suppose that the last 2, okay, are equivalent to one another, and N1 be equivalent to N2. And in short, we use this 3 parallel bars to show equivalence of 2 one-ports. Okay. Then, for both of the following configurations, instead of branch currents and voltages within N0, the first one port, will be the same. Okay, here we have N0 with terminals labeled A and B. Here we have, okay, the replica of the same circuit N0 with terminals A and B. Okay. And if we have a pair of one ports, we're calling them N1 and N2. They could be very different inside, but at the port terminals, they display identical current voltage characteristics. Okay, so therefore, according to our definition, they are equivalent. So if N1 and N2 are equivalent, and then in the first configurations, you connect N0, N1, and then here you connect to N0, N2. Okay. And N1 is equivalent to N2. And then in both of those configurations, inside N0, everything will be exactly the same. Okay? If you're just sitting inside N0, therefore, you cannot determine whether you're connected to N1 or N2 or N3, where N3 is equivalent to N1 and N2 and so on. Okay. So we already know, without knowing that we know, some equivalent one ports. Okay, so let's remember them quickly, and then we will move on to some other examples. Okay. Some equivalent pairs of one ports. Okay. Suppose you have the following one port where K LTI resistors are connected in series. Okay. So this circuit, this single circuit, is your one port. Let the resistance of the first resistor be R1, the second be R2, and so on. The last one be RK. Now we know that this one port, which inside has K components, K LTI resistors, can be represented by a single component, one port, and the two one ports will be equivalent. Okay, so that's equivalent to one port circuit with just a single resistor if the resistance of that resistor is chosen to equal the sum of those K resistances. Okay, are equivalent. We're calling that resistance, or sometimes it's called R effective. Okay, and that's R1 plus R2 plus RK. Okay. So if N1 is this and N2 is that, then what we can do is we can just take N1 out and plug in that single resistor, and that inside N0 everything will still be the same. Okay. Now this is series connection with resistors. We can do, so let's call this A, B. You can do a similar thing for independent voltage sources. Okay, so suppose that we have a bunch of independent voltage sources connected in series. Okay, A, B, plus minus, plus minus, plus minus, and so on. This is VS1, this is VS2, this is VSK. This is the voltage supplied by this source, this is the voltage supplied by that source, and so on. And all those sources are connected in this series fashion. And again, it's almost immediate that those K independent sources can be represented by a single independent voltage source, provided that the voltage given by that single voltage source equals the sum of all these individual voltages. Okay, so that's equivalent to A, B, VS equivalent, let's call it, provided that this voltage is chosen to be VS1 plus VS2 plus VSK. Okay, this type of equivalence has a name, it's called, or connection, it's called series connection. Okay. Now we have the dual connection, namely the parallel connection. Let's also quickly remember that. Now, suppose you have a bunch of resistors, but this time those resistors are connected in a parallel fashion, by which we need the following. Okay. This is R1, this is R2, this is RK, LTI resistors. And this one port, which contains K individual components, can be represented by a single LTI resistor, provided that the resistance of that resistor is such that R equivalent is 1 over R1 plus 1 over R2 plus 1 over RK inverse. Okay. Or in terms of conductances, it's much easier to express this equivalence. Here we have a bunch of resistors with conductances, let's say G1, G2 up to GK, and GK is 1 over RK. Okay, G2 is 1 over R2 and so on. Therefore, G equivalent is the sum of individual conductances. Okay, G equivalent equals G1 plus G2 plus up to GK. So that's called parallel connection. You can do the same thing with current sources. This is ISK. IS1, IS2, A, B. This is your one port that has K individual independent current sources connected in parallel. It's not difficult to see that this connection on this one port can be represented by an equivalent one port which uses only a single independent current source, provided that the current that's supplied by that source equals the sum of individual currents in this, the first one. So this is equivalent to A, B. This is IS equivalent, and IS equivalent equals IS1 plus IS2 plus ISK. Okay. And this type of connection is called parallel connection. Okay. Parallel connection of current sources, parallel connection of resistors, series connection of resistors, series connection of voltage sources, and so on. Okay, now these are more or less obvious. Let's see another less obvious equivalence between two one ports. And later on, that type of equivalence will be quite useful when we study Thevenin and Norton equivalent circuits. Okay. Now, consider two circuits or two one ports. Okay. A, B, plus minus Vs. This is R1. Now, here is a one port, here is another one port, and two one ports are connected as follows. Now, the one port that we want to study is the one on the left, okay? This is our one port. With port terminals labeled as A and B. Okay. Now, let's label the port voltage and port current as V and I respectively. Okay, so this voltage here is the port voltage of R1 port, and let this current, which we label I, be the port current. Okay, for R1 port. Now let's figure out the IV characteristics of calculation between current and voltage. So it's easy in this configuration. So this voltage, let's express one in terms of the other. This voltage by KVL equals the sum of two voltages. This voltage across the terms of the resistor, plus minus, plus this voltage of the independent voltage source, plus minus Vs. Okay? So this voltage is plus minus R1 times I by Ohm's law. Okay? Therefore, this overall voltage equals R1 times I plus the voltage of the voltage source Vs. So V equals R1 times I plus Vs. And this is, we assume that R1 and Vs are given or known. This equation is what we call the IV characteristics of this particular one port. Okay, so let's give it a number. We're going to call it equation 1 or relation 1. Now let's study a different one port. This time we have a current source, and to it connected in parallel, and again an LTI resistor. Okay. So this is IS, the current of the independent current source. This resistance we're calling R2, and here we have A and B. And and suppose that it's connected to something. And what it's connected to is not important for our purpose at this point. So let's use the same letters to label the voltage and current of that new one port. This is the port voltage, and here this current is the port current, labeling as I. Now for that one port, let's also figure out the relation between voltage and current. It's also easy to figure out. This voltage directly equals the voltage that appears across the terminals of the resistor. Okay. And what's the voltage of that resistor? Plus here, minus here, it's R2 resistance times the current passing through this direction, that resistor. Okay. And then what's the current passing through that resistor in that direction? I is coming from here. Here's another incoming current, IS. Therefore, this current must be I plus IS by KCL. Okay. So, voltage, this voltage equals R2 times the current passing through R2, which is I plus IS. Therefore, V equals R2I plus R2IS. Okay, so that's the IV characteristics of the second one, and we gave it the number 2. Okay. Now, what we have figured out is the following. So let's rewrite it in a clean fashion. So, in summary, the one port plus minus Vs R1 A B plus minus V, and this current is I. So this one port has the IV characteristics given in equation 1. Okay. And likewise, the other one port, the one port on the right, this is I, this is V, R2, and this is IS. And this one port has the IV characteristics given in equation. Okay. And now, since everything is clearly figured out in terms of the relation between voltages and currents, now we can apply the definition of equivalence and find conditions on the parameters of this one port and the parameters of this one port, so that under those conditions, those two one ports become equivalent. Okay. So, equivalence means same IV characteristics, and when we look at equation 1 and equation 2, it's easy to see under what conditions on the parameters those two equations become identical. Okay. Here we have V on the left-hand side of both equations. Therefore, equivalence should imply that this right-hand side and that right-hand side are equal. In order for this right-hand side and that right-hand side to be equal, it's clear that R1 must equal R2, and Vs must equal that R2 times Is product. Okay? So under those conditions, two one ports become equivalent. Now, if we take R1 equals R2 and Vs equals R1 Is or R2 Is, because R1 and R2 are now equal, then 1 and 2 become identical equations. That is, two 1 ports under this condition would have same IV characteristics. Hence, under those conditions, 1 ports become equal. Okay. The numerical example is as follows. Suppose this is our 1 port with a constant voltage source, a battery, connected in series with an LTI resistor with resistance 10 ohms. Okay. And then we want to represent this with a current source connected in parallel with an LTI resistor. Okay. A, B. And the question is, how should we pick the current of the current source and the resistance of the LTI resistor? And here is the answer. Choose the resistance here, same as the resistance in the first 1 port. Okay. This port becomes 10 ohms. And then choose the current source such that, choose the current such that the current times the resistance gives you the voltage that's on in the first 1 port. Okay. Therefore, the current must be a constant current of 2 amps. Now, that was certain basics that we will find very useful in the following lectures. Now we're ready to start talking about solving LTI resistive circuits. Okay? So solving LTI resistive circuits. Okay? By which we mean, as we said, figuring out all the currents and voltages for a given circuit. And for that, we will talk about 2 methods. One of the methods, there are 2 methods. Okay. One of the methods is, in order to solve the circuit, first formulate it in terms of node voltages. Okay. And that's called node voltage analysis. The second method is the dual of the first method. That is, in the second method, we will see how we can formulate the circuit in terms of mesh currents. Of course, in order to be able to apply the second method, the circuit must have a planar graph. Okay? But if that condition is satisfied, this method is as powerful as the first one, mesh current analysis. So that will be our first method, second method. Okay. Now, in the next lecture, we will continue with talking about the first one, node voltage analysis.